Okay, next in part one of this lecture, we're going to look at what's called outliers, leverage, and influence. So essentially what we're going to look at is when we have extreme values and influential observations. So having discussed ways of improving model specification globally through a transformation, what we're now going to look at is whether individual observations within the data themselves may be unduly influencing the fit of the model. And I'm sure everyone watching this video will have heard of the expression outlier before and will understand approximately what an outlier is. So what we're really concerned about here is a situation in which a small number of extreme values in the data may unduly influence the fit of the model and therefore the magnitude of the parameter estimates. And the diagram in this slide shows two examples of where that's happening. So on the left-hand side, relative to the sample, one observation here has an unduly large value of y, given the general relationship between x and y that we see in the main mass of the data shown here. So this observation here has a large y value. On the right-hand side, relative to the sample, relative to the mass of the sample, one observation has an unduly large value of x. Its y value isn't unusual, but its position in the x space is. And the impact that such observations can have on the regression coefficients or in the overall fit of the model is generally referred to as influence. And the two features of the data that characterize influence, what we call outliers and leverage. And I'm going to discuss each of them in turn. So let's look first at outliers. Outliers are points for which the response datum y is far from the model prediction y hat, resulting in a large residual. So in the diagram, we fitted a regression line and we have an outlier shown here at the top. And the question is, what influence is that point having on the fit of this regression line? Is it pulling this line in a particular direction? Now, outliers can arise for a variety of reasons. It could be they've been recorded incorrectly, simple measurement error or data entry error, or they could actually be observations that simply don't belong to the same population as the rest of the data. So when we see this kind of large residual on one or a small number of observations, the question is, what do we do about it? Well, the first point to say is that outliers should almost never be discarded simply for being outliers. The fact that we have an outlier actually might be telling us something important. So they may contain relevant and crucial information about the process under consideration, or they may also indicate a deficiency of the model, such as a missing predictor or some other specification problem. Maybe the model, maybe the mathematical form of the model, maybe the curve that we're using is not correct. And actually, there's two examples often quoted in which, had outliers have been discarded, the inference from those models would have been deficient. The first concerns the detection of ozone depletion. So the Antarctic Satellite Data Collection System automatically deleted outliers, and as a result, the hole in the ozone layer was detected much later than it could have been, apparently. A second example often quoted concerns the discovery of the atomic nucleus. So had Geiger and Marsden discarded the outliers in Rutherford's 1909 experiment, the alpha particles detected at extreme angles, the nucleus of the atom would have gone undiscovered. So outliers can contain important information. They can be extremely scientifically valuable, but large outliers should always be investigated further to check the sensitivity of conclusions to these points. So that's outliers. The second characteristic that I want to talk about is leverage. And leverage occurs when observations have an unusual predictor vector x given the response y, giving them potentially undue influence over model fit, and this is shown here. In the diagram, the point on the far right has an unusual x value, And you can see it is pulling the regression line down here. It's pulling the regression line towards itself. And if that estimate wasn't there, we'd probably fit a steeper line and we'd fit a line with a better fit. Note that an observation can be an outlier or a high leverage point or both, or neither. They're distinct concepts. And as with outliers, leverage is worth investigating because any data problems with points of high leverage may invalidate the entire fit of the model. So how do we detect and diagnose leverage? Well, to do so, we're going to use the residuals written here, EI equals YI minus YI hat, which as usual, we're going to distinguish from the true disturbances which we don't observe. Now, in order to understand a bit about influence, we're going to have to go back to some of our matrix theory from lecture 5. So in lecture 5, we introduced the hat matrix. And using the hat matrix, we can write the residual vector as I minus H times Y, where H is equal to X, X transpose X inverse, X transpose. That's our hat matrix. In this context, H is also known as the influence matrix because, as we'll see, it's going to tell us something about influence. Now, H is symmetric, so it's idempotent, and it has elements H, I, J. So, substituting the model into the definition of the residuals gives E equals I minus H times epsilon. So we've written our residuals in terms of the true disturbances, or element by element, EI equals epsilon I minus a weighted sum of all the disturbances. So this shows exactly how our estimated residuals differ from the true disturbances that we don't observe. Now, a useful feature of the influence matrix is that we can write each fitted value as a weighted sum of the observed responses with weights given by the elements of the hat matrix. In particular, HII, the ith eigenite element, is the weight of YI in the expression for its own fitted value. It is the influence of YI on its own fitted value, and HII is known as leverage. So we'll consider three useful metrics that measure an observation's influence using information from the residuals and the leverages. The first is called the standardized residual. This is the transformation shown in definition 2. The residual divided by S times the square root of 1 minus HII. It describes the number of estimated standard deviations by which YI minus YI hat I depart from 0. Under homoscedasticity and normality, the standardized residuals should all behave like a sample from a standard normal distribution, so nearly all of them should fall between about -3 and +3. Values outside that range are going to flag potential outliers. So that's our first diagnostic statistic, the standardized residual. The second is called Cook's distance, which quantifies the change in fit when an observation is removed. If Y hat is the vector of fitted values using all the data, and Y hat sub I is the vector of fitted values with the ith datum omitted, then Cook's distance, D sub I, is the squared distance between them scaled by k+1 times S squared. Notice from the second expression on the slide that DI combines both ingredients of influence. It's increasing in the standardized residuals and in the leverage. So a large DI, say 3 times the mean of D's, indicates an influential observation. And the third metric we're going to look at is the leverage itself. These are the diagonal elements of the hat matrix, and leverage measures the potential of extreme predictor values to influence the model fit. So the slide gives a useful way of writing HII in terms of the mean-centered model matrix. Don't worry too much about the algebra. The point is that the squared deviations of the elements of Xi from the mean of the variables appear in HII. It's shown here. So leverage increases then as xi moves further from x bar, the centre of the covariate space. The leverages have a mean of k plus 1 over n, and as a rule of thumb, a leverage greater than about twice that mean may be considered influential. So that's what I've tried to do here. Is I've tried to show you some diagnostics. I've tried to give you a bit of the algebra underpinning them. That's not what's important. What's important is to understand the principle of outliers, leverage and influence. And what we're going to do in the tutorial is we're going to return to the estimation of Hubble's constant that we looked at using the Hubble data. We're going to check for evidence of undue influence arising using these three diagnostics. So the standardized residuals, Cook's distance and leverage. And then we're going to re-estimate the model, excluding influential points, to quantify their effect on our conclusions. So far, we've focused on observations that influence the fit of the model. We're now going to turn to a different issue. We're going to look at whether the explanatory variables themselves contain enough independent information for their individual effects to be estimated. And that's under this topic known as multicollinearity.